So yeah.
Yeah. So our afternoon session will contain the talk by Marc, which will be followed by the poster presentation at 3:30. Yeah. In the next room, which is called discussion room. So I'm happy to introduce the talk by Marc Lelarge, who is working at Henrietta for Normale Superiore, and he will speak about matching and ranking for random. How do diluted? Diluted graphs. Okay. Thank you.
Thank you, Sergey. So I will explain the terms in my title during my talk. So I'd like first to thank the organizer for giving me the opportunity to present my work here. And this work is a joint work with Charles Bordenave, who is working with CNRS in Toulouse, and Justin Salez, who is working with me at INRIA, and is a PhD student. So in my talk I will speak about 3 stories. Okay, here are the 3 stories, which are closely related, I think, but belongs to different fields. So the first one is belongs to the field of combinatorial game theory. The second one is just linear algebra, and we will use tools from random matrix theory. And the last one is combinatorial optimization problem. We will have the point of view of statistical physics for this one. I'll try to explain you why these 3 problems are related. So let's start with the first one. So I have to acknowledge Johan Westlund, because it's a very recent talk I saw from him, who inspired me for the first part of this talk. So I don't know if you are familiar with what people call geography game. So I will take a very simple instance. It's a 2-players game, so Alice and Bob are playing. Alice will always play first and Bob second. And the rule is fairly simple. You have to name, for example, capital or cities in the world. And the first one who is not able to give a name will lose. And there is a simple rule that the starting letter of the capital you tell must be the same as the last one of the previous player. Okay, so if you start with London, then you have to find another capital, say in Europe, so Nicosia, for example. So Alice is saying London, Bob is saying Nicosia, then Ankara. That's a nice one, because you have to find another one with A. And of course, you are not allowed to use Ankara anymore. Okay, so let's say Amsterdam, Madrid, Dublin. And here, you have to find a city starting with the N. And of course, you are not allowed to use Nicosia. Okay, but well, you have to set the rule properly, but I guess you follow me. Say Dublin is allowed. So, but here the point is, after Dublin, you are not allowed to say Nicosia again. Okay, so if you want to stay in Europe, you are done and you are stuck. So you will lose.
Which was the capital of a divided country?
And then you have to go to India, for example, to continue the game. Okay. Since you are on a finite, you have a finite number of possibilities. If you are just setting, there will be a winner at the end of the game. The last one who is able to tell the name of a city. Okay. So I will look actually at even simpler version of this. So I will consider a general graph. So here the graph will be, the vertices of the graph will be the name of the city, and you put an edge between 2 vertices. It's the last letter of the capital name correspond to the first letter of the other vertex. Okay. So this is your graph. You still have Alice and Bob playing on this graph, and each time you move to a new vertex, you remove it from the graph. Okay. And whoever gets stuck will lose. So here, in the previous example, I was considering a directed graph, so edges were directed, and I'm considering the simplest version where you are allowed to use edges in both directions. So it's undirected vertex geography, meaning undirected is clear, and vertex means that each time you move to a vertex, you remove this vertex, and you are not allowed to use it anymore. Okay? Vertex.
This means you can give a capital that ends with the first name of the city.
Yeah, it's not exactly the game I just described, but this is the model we consider. So you are doing a self-avoiding walk, right? Okay? And the assumption about the information is that all players know everything, so they know the graph, and here there is really nothing random, it's a pure strategic problem. Okay? Starting from a vertex, you can say whether you will win or lose. That's completely done. So here comes the randomness. I will play this game on a Poisson-Galton-Watson tree. So this is a standard branching process. And I will consider in this talk quite often random rooted tree. So there is a particular vertex which is called the root, and I will represent it at the top of my figure. And for the Poisson-Galton-Watson tree, this means that the offspring distribution is just Poisson with parameter lambda. Okay? So Alice starts at the top of this tree, and then you are moving downwards the tree. Okay, so what is the best strategy on this tree? It's fairly simple to work this out. You clearly don't want to be at one of these leaves because otherwise you are stuck. So the red vertices are vertices where you are sure to lose, and the green one are vertices where you are sure to win. Okay? Because when you are at a green vertex, you just have to move to a red one, and then the other one will lose. So now if you are the root, it's clearly not... Is there a pointer somewhere? Or
Whatever.
So if you are the root, it's clearly not optimal to choose this edge because then Bob will be in a winning situation. Okay? So what you can do is just remove this edge because you don't have to consider it if you are Alice. And here is the optimal move that I did plot for Bob if you end up in this situation. But what I did with this green vertex is also the case for all other green vertices, and you can remove all the leaves like that. Okay? And you end up with such a situation. So now Alice has only two choices left, and you can do you are exactly in the same position as in the first one. You have two leaves, so you don't want to end here, and here is a possibility for Alice to play. So at the end, here is an optimal strategy for Alice. You just move to this one, and then whatever Bob will do, you will end up in a dead end. Okay. So you see here that there seems to be a connection with matchings because the blue edges correspond to a matching of the tree. But I will not need it right now. So
Why did you connect this blue line to the right, not to the left?
here,
Yeah.
you can do it either way. So it's working. So you have to choose, but it will be important in what follows. Okay, so here is just a picture of what you have done. If you do the calculation, you try to compute P, the probability that Bob wins under optimal play. So this is just the probability that the root is color red in this coloring of the tree. So it's fairly simple to work out because you have a nice branching property. So if you compute P, that's the probability that Bob wins. So this means that all children are green. Okay? Meaning that whatever you do, you will end up in a winning situation for Bob. So this is exactly the probability that no child is red. And this is a Poisson process with red lambda P. So this is exactly e to the minus lambda P. Okay? This is a simple consequence of the branching property. And if you solve this fixed point equation, you have this well-known expression where this is a Lambert function. And if you plot it, it's a curve like that as a function of lambda. Okay, lambda is the average degree of your graph. So when lambda is very small, the probability of Bob of winning is quite high, meaning that you might have a single node only, and then it decreases like this. Okay. So the title of my talk is A Naive Guess, and there is a reason for that. The truth is that this curve is not correct, this one is correct. So there is something happening between 2.5 and 3. I'll try to explain you.
It's called E, right?
It's called E, so good guess from... exactly, there is only one number between 2.5 and 3. So, yeah. So what happened in this game, it's fairly simple to explain. What I did in the first slide was just this equation, which is the solution of the fixed point equation of this map. But what you should really take care of is of iterating this map. Meaning that you should look at the game when you play on a truncated tree. So when you truncate the tree after k moves. Okay? So now I compute p sub k. The point is that Bob wins, so the same thing, but when you go only to depth k in the tree, you are not allowed to go further. So clearly P0 is 1, because you have only one vertex and you are sure to win because Alice has no move. Okay? So P1 is what? It's just that the probability is that the offspring of Alice is 0. Okay? So this is E minus lambda. And again, thanks to the nice branching structure of the tree, you can compute P sub k plus 1 in function of P of k. So P of k plus 1 is the probability that Bob wins in the tree truncated after k plus 1 moves. So this is exactly the same as Bob loses from any child of the root in the k truncated tree. And you can rewrite it like that, because each time you have independence in the subtrees, where n is a Poisson random variable with parameter lambda. So this is the offspring of the root. Okay? So P of k plus 1 is just the iterate of the map E minus lambda P at times Pk. Is that clear? So now, here is the picture. So this is my map on the identity thing for lambda equals 2.5. And here is what happened when I do the iteration. So I start from 1, okay, P0 equal 1, P1 is something, and so on, and it seems to converge to the fixed point. Okay, so that's okay. Now I'm taking the same curve, but for lambda equals 2.9. And here is what happens. So you see that it does not look like it converges to the fixed point of the original equation, and the reason is that you are iterating a decreasing function, and you know that in order to have increasing subsequences, you have to iterate twice, and you introduce other fixed points, which are these two. Okay? So what does this mean for the game? Is it's not clear from this picture. I'll try to explain it to you on this one. If you do the leaf removal, so this is the first coloring algorithm I explained to you about the graph, coloring in red and green. What you were doing is each time, at each iteration, you were removing the couple of red and green vertex. So this is what I call the leaf removal algorithm. But now you consider a possible infinite tree. So I'm taking, this is just the depth 4 version of the tree, but it does continue perhaps to infinity on this path. Okay? So the real leaves are only these two guys. So when you do the leaf removal on this graph, you are just allowed to color in red these two guys and not the other one. You are not allowed to touch the path going to infinity if you want. Okay, so if you do that on the same iteration as I explained you on the finite graph, then you still can remove this edge, but then you are stuck. Okay, and what you can show is that when lambda is less than E, if you do this leaf removal algorithm on the infinite tree, then you will always be able to reach the root. So you will be able to color the whole tree. Whereas for lambda bigger than E, then this situation will appear. You will have with a positive probability that the root belongs to an infinite path that is never touched by the algorithm. Okay, and so this is what we call the core of the tree, and it appears exactly at lambda equals e. Okay, so when you do the leaf removal algorithm on the infinite tree, then it might happen when lambda is bigger than e, then something remains after the leaf removal. Whereas this does not never occur on a finite tree, of course. Okay, and now what are the implications for the game? Well, if you start the game outside the core, then you can do the leaf removal and you know who will be the winner. But if you start inside the core, this means that there is an infinite sequence of optimal moves, and player will always stay in the core. And basically, the parity of k, if you play the truncated one game, will determine the winner. Okay? Because in this case, moving out from the core means that you will lose the game. Okay? So this is what happened. So here is perhaps a better picture for the probability of winning for Bob. So until lambda equals e, it's this nice function. And then in this whole section, there is what you could call a draw, so meaning that the game will go forever in this whole section. And you are not able to determine who will win. So in this case, this sub-area, Bob is winning, this one, Alice is winning. And here, there is an infinite sequence of optimal move. Okay? So, for me, the draw means that if you consider the truncated game, the boundary condition will always matter for the probability of the route being winning or losing. In this case, it's very simple. If k is odd, then I don't know, Alice or Bob will win, and if k is even, then it's the opposite. Okay. So is that clear? So this was I will come back to this game at the very end, but now I'd like to move to another problem, which is just linear algebra. So you can almost forget everything I told you so far. Sorry. So here are some notations. So I'm considering a graph Gn, okay, with n vertices, and A sub n is the adjacency matrix of Gn. So you put it's a 0-1 matrix, and you put a 1 whenever you have an edge. So this is a symmetric matrix, so you have real eigenvalues, which are denoted with multiplicity like that. And what I'm interested in is a spectral measure of what I call the graph, which is just the empirical measure corresponding to these values. Okay. And the rank of the graph or the rank of the matrix is just 1, so it's a normalized rank, it should be, okay? 1 minus the size of the kernel divided by n. Well, okay. So these are the objects. Sorry? I'll come to that.
Excuse me, what
And
is
it won't be true.
No,
No, I mean, for trees, it's completely
I come to that.
independent what the limit is.
So the question I'm asking is if I consider a sequence of graph whose size diverges to infinity, and if it converges in some sense to a limiting graph, do you have convergence of the empirical measure of mu n, the spectral measure? So I think that's related to what you expect. Is it related to the spectral measure of, in a sense, of this graph? And do you also have the convergence of the rank? So these are the three questions I'm interested in. So there are some known results. So here is, I guess, the oldest one in this case. If you consider for Gn a sequence of random regular graphs, okay, so everybody in the graph has degree d, which is fixed and does not go to infinity as n tends to infinity. Okay, so you take uniformly at random a graph among all possible graphs with degree d and with n vertices. No, you look at this graph and you can show that the spectral measure will converge to this Kesten-McKay measure. So this was proved actually first by Kesten and then by McKay more closely related to this context. So this is an absolutely continuous measure with respect to the Lebesgue measure, and you have the explicit density in terms of D. Okay. So you see here that it's not at all the semicircular law, but if D tends to infinity, then this will oppose the semicircular law, for example. More recently, there are some nice results from Korunzny, Srebina, and Wegerowski, who did the same kind of work for Erdős-Rényi random graphs. Okay, so I will define this a bit later. So but they have no explicit formula for the limiting measure, but still they are able to characterize it. And there are also some results for trees. So first from physicists who did exactly the question of the rank, so the one I'm also interested in, for uniform spanning tree on the complete graph. And there are some recent results for Bamedi, Evans, and Sen, but for growing trees. Okay, so it's not really for graphs.
Can you go to the previous slide, please?
Sure. Previous one?
Yes. The one after that. Thank you.
Okay. So first, there is a nice connection between the leaf removal algorithm and the rank of the matrix. So here is a picture of the leaf removal algorithm for any graph. Okay. So you have to go this way, and then here. So you start by picking a leaf, its only neighbor, and you remove everything connected to these two guys, all edges. So you end up with one isolated vertex on this subgraph. Then you have another leaf here, so you pick that one, and you remove these two ones. This procedure will create a new leaf, and you iterate like that. So this is the core of the graph, which is a subgraph of your original graph with mean degree 2. Okay? And you have some isolated vertices, here only one. And it's very simple to show that when you move from this graph to this one, you will not change the dimension of the kernel. Okay? So the size of the kernel of the adjacency matrix of this graph is exactly the same as this one. But so basically, it's the same as this one and this one. So there is one part which is fairly simple to compute, is each time you have an isolated vertex here, this will correspond to an eigenvalue 0. Okay? So you have this very simple relation. The dimension of the kernel of your original graph is just the number of isolated vertices at the end of this leaf removal algorithm, plus the size of the kernel on this. This is just due to the additivity of the kernel.
This picture, when you remove the guy, top right,
Here?
why didn't you have a triangle left behind?
You take away the node also.
You
Why-
took away the red node, but bottom was
The red on the black, and
you
all
take-
edges connected
you
to
take
these
all
two.
edge.
Yeah,
You
all
take-
edges connected to these two guys.
You're basically doing sort of matching. Yeah.
Yeah, exactly. I can do that. So it does create a matching if each time you take the red with the adjacent one. Though the nice thing is that if you do it for a finite tree, then you know that the leaf removal will end up with an empty core, and you have an explicit formula for the size of the kernel of your tree. Okay. So here is a small exercise. What is the size of the kernel for this tree? So this is exactly the same tree as I did for the first game, geography game. Yeah, dimension, okay. 6? Dimension, sorry. The reason.
No space. Yeah, 3.
So the size of the kernel is just the tree, the number of isolated vertices when you do the leaf removal. Okay? So this is just a rating of this formula. So, but in general, if you have a general graph, then you, with this leaf removal algorithm, you will only get a lower bound for the size of the kernel, okay? Because you are just discounting this term. Okay, but for trees, it's working asymptotically fine. So the hope is that it will still work for graphs which converge to locally to trees. So these are the type of graphs I will look at. So this is why I call it diluted in my title, because I'm assuming that the average degree is finite, okay, in my graph. So when n tends to infinity, the degree distribution of each node tends to a proper distribution. It does not go to infinity. Okay, this corresponds to the diluted version. The dense one would correspond to the case where this degree will tend to infinity as n, and the sparse one as log n, for example. Okay, so this I will only consider the diluted one. So if you take the standard Erdős-Rényi random graphs where you put an edge between two vertices with probability p independently of each other, you have to choose p in this way as n tends to infinity in order to get a diluted graph. And then the limiting degree distribution will just be a Poisson distribution with parameter lambda. Okay, so this is the local limit is the Poisson-Galton-Watson tree I just described you at the for the first game. If you take the uniform measure on the irregular graph, then this will work also, and the degree distribution will be just a Dirac mass at D. And you can consider a more general distribution. So this is the model called configuration model, where you prescribe a degree distribution, so you know which distribution you want to achieve for the degree, and then you take uniformly at random a matching among them. So it's not very important how you build these graphs. The only thing I want to emphasize is that for all of these graphs, if you take a random vertex in this graph, okay, random meaning with probability 1 over n, you pick a given vertex. If you look at the ball of radius t, where t is fixed, and you let n tends to infinity, then what you will see is with high probability a tree. And this tree is actually a Galton-Watson tree, with the original distribution being exactly that one. And then you have a size-based distribution for the other offspring. So this is a standard argument in random graph. So in the case of Erdős-Rényi random graphs, what you will see is just a Poisson-Galton-Watson tree. Okay.
In your last example, you allow self-loops and multi.
Yes. So actually, it's not a matter. You can condition on not having a self-loop and things like that. When n tends to infinity, under proper condition on the moment of pk, you can show that the probability that your graph is simple does not go to 0 as n goes to infinity. So you can take a condition on this event. The only thing that will matter for me is that locally it will look like a tree. Okay, I don't want to be more precise than that. So since I have a local version of my tree, the first thing I like to do is express the spectral measure as a sum of contribution of each vertex. Okay, and this is done in this slide. So it's basically linear algebra. You have a symmetric matrix AN with the eigenvalue given by lambda I, and B is just a basis of eigenvectors, and you can, in a sense, decompose the action of AN on X like this on each of the eigenvectors. And then I'll define the spectral measure of the graph when rooted at V. And if this expression is not clear, that one might help. This means that whatever function you take of AN, and you look at what it will give on the basis eigenvector associated to the vertex v, okay, is given by this integral. Okay, so this is standard Borel calculus. I mean, so, and if you work out this function, you end up with this expression. So you have an explicit formula of the spectral measure of Gn rooted at v in terms of the eigenvectors and the eigenvalues, of course. Okay. So in a sense, you see that this spectral measure takes care of all the contribution of the vertex v for your matrix A. And you can rewrite the empirical distribution like this. So it's still 1 over n on the sum of n term, but each term corresponds to a vertex of your graph. So here you should look at this quantity as first you pick a vertex at random with probability 1 over n, and then you consider the measure associated to this vertex. And this is the right way to look at your spectral measure in order to show that this will converge. Okay. So now it should not come as a big surprise that it's fairly simple to show that you have convergence of this object to basically the average object on the limiting graph. Okay. So this is what I wrote in a non-waving argument here. So the problem is that the limit of your graph might be random also. Okay. For example, in Erdős-Rényi random graph, you end up with Poisson-Galton-Watson tree. And because of this 1 over n, the empirical measure will converge to the mean value associated to the spectral measure of your tree rooted at the root. Okay? So this quantity is just the spectral measure of your possibly infinite tree taken at the root. Okay? And you are taking expectation in order to get the proper limiting object from UN. So the nice thing with this theorem is that it will give you an upper bound on the size of the kernel. Basically, since you have convergence of this for the standard weak convergence, if you look at an atom, you have an upper bound for the measure of an atom at 0. Okay.
So, sorry, Mark, can you say some more about what mu sub t is? I mean, it's.
Yeah, I come to.
I mean, now we got this infinite graph,
yeah,
right?
So I come to that in one moment.
All right. So you're going to say.
Yeah. So basically, what I'd like to just to say before going to that is, if you are able to, so this was the lower bound for this quantity. So if you are able to show that, and it's fairly easy to compute. I mean, this is just an analysis of a leaf removal algorithm. If you are able to show that this quantity and this quantity agrees, then you are done with the convergence of the rank. Okay. So what remains is to compute this quantity. That's what I will concentrate on. So here is probably an answer to your question. So now I'm forgetting about the graph. I'm working on rooted trees, so T, and even Galton-Watson trees, meaning that you have a branching property. And now you have possibly infinite graph, okay? So it's not possible to speak about matrix, but you have to speak about operator associated.
So this is on little L2.
Exactly. L2 of V.
Yeah. Okay.
Or N. Yeah. And so this operator, of course, is symmetric. So I mean, that's obvious. But since you are dealing with infinite dimension, it's not always self-adjoint. And you can show that if you have a finite branching for this tree, then automatically the operator will be self-adjoint. And the nice thing is that once you know if it's self-adjoint, then you have a spectral measure associated to the root. So, and this is exactly my model of T. Okay. Does it answer? Yeah?
But yeah, that's
So now, remember what I'd like is to compute this. Well, the atom of this measure at 0, the expected value of this random guy, because T now is random. So I will do that using a kind of standard random matrix theory. So this is what is called a Cauchy-Stieltjes transform of a measure. So this is the definition. So if you never saw that before, it's a kind of Fourier transform for your measure. So if you give me a Stieltjes transform, I can invert it and go back to the measure, basically, under non-restrictive assumption of me. And it can be rewritten like that. So it's the resolvent of the adjacency operator of the tree. Okay, so if there is no difference with the finite case, since you know that this guy is self-adjoint, you know that for any z with a positive imaginary part, this will be invertible. Okay, so that's fine. And you are taking it at the root, so I'm denoting it like that. Okay, so this is the first coefficient of this matrix, if you want. First line, first column. And now, what is important for us is that since we want to compute this, by using this formula, you can show that it's given by this limit as t goes to 0 when you are on the imaginary axis for the Stieltjes transform, okay, and you let t goes to 0. So this is really what these quantities that I'd like to compute. And now I'm using a basic linear algebra calculus, which is Schur's identity for the finite dimension case. If you want to invert this matrix, then you have this explicit formula for the first coefficient. Okay. And well, you can show that you can apply exactly this kind of argument even for your operator, and you end up with this formula. So this is a Stieltjes transform of the measure, which is exactly the coefficient on the first line, first column, so this b minus 1, 1, 1. Okay, and you apply exactly this term, this formula, and you see that b tilde corresponds to the in terms of the graph. Okay, this will correspond to a tree where you remove the root. So this is what I denoted like that. So you remove the root from the tree, and you look at the component v, where v is a neighbor of the root. But since you are on a tree, each one of these components will be subtree that I denoted t of v. Okay, so you have this nice recursion that the spectral measure of your original tree is given in terms of the spectral measure, the Stieltjes transform of the spectral measure of each of the subtrees. Since you are dealing with a a Galton-Watson tree, you know that these guys will see exactly the same things below them as this one. Okay, so in a sense, they are IID with the same distribution as this one. Okay, so you end up with a fixed point equation, which is called RDE, the recursive distributional equation. And this is exactly the previous line I showed you in terms of distribution. So here I'm working on a bit complex space. I'm working on the set of holomorphic function from C+ to C+ satisfying this condition. You can show that any Stieltjes transform will satisfy this condition. Okay, so this is a nice set because it's compact. And so I'm looking at law, probability law on this set H. Okay. And what you can show is that this recursive distribution equation completely characterizes the law you are looking for. Okay, there is a unique solution for this equation. So here n is just the offspring distribution in your tree. And since there is a small bias between when you are inside the tree or at the root, here is an explicit solution for the root where n star is the degree distribution, exactly the degree distribution, while this one is the size-based distribution. Okay, so for heterogeneous random graph, it's just Poisson. Okay, so this is a characterization of the Stieltjes transform. So now what I want is compute this limit. So I'm just taking the imaginary part of the Stieltjes transform on the imaginary axis. I'm applying exactly the recursion I gave you before. I obtain this for EOT. I'm iterating once. on multiplying by t, because this is the limit I want to look at. And if I look at the limit, I end up with this recursion. So I started with a recursion on the space of holomorphic function to a recursion just of random variable on 0, 1. I have to solve this equation. So this is doable, and it's written in this slide. So there is a function f which depends on the degree distribution, and there is a one-to-one map between the what we call historical record of f and the solution of this RDE. So each time you have a historical record, meaning that it's the first local maxima that have never been reached before, okay, starting from 0. You are able to compute the mean on everything for the fixed point equation, for the RDE. So if you go back to the case of Erdős-Rényi random graph, so phi is just the degree distribution, sorry, is just a Poisson random variable with parameter lambda. You are able to compute this. You are able to compute this because this is the shape of the function f, and you see that there is only one. Well, there might be several maxima, but there is only one historical record. So the RD has only one solution. So you are able to compute this quantity, and it's exactly the same as this one. So you are done in the case of Erdős-Rényi random graphs. There is an open problem. So basically, what happens when you have more than one solution to the RDE, and the lower bound will tend to the smallest solution of the RDE, whereas your upper bound will tend to the largest one, and you don't know where you are in between the gap. So this is one example where it does happen. Okay. Is there any questions so far? So now I'll go to the last story, hopefully. So here is just a definition of what matching is. So if you consider your graph, so I will consider a graph where a matching is just a subset of edges with no common vertex. And I'm interested in maximum matching, meaning that you have a maximum number of edges or a minimal number of uncovered vertices.
So can I actually maybe ask a question? Where in that were you actually using the fact that it was just the amount of mass at 0 that you were computing? Why doesn't it give you other
so this
other atoms?
This gives you everything. I mean,
right,
it's
yeah.
completely correct as the CS transform. The thing is, once you try to compute things based on this equation, it's quite hard. And the one thing that we are able to do is just looking at this recursion on the imaginary axis, and it's amplified
Right.
to these things,
Yeah.
and then you end up with a recursion on basically on 0, 1, on random value on 0, 1, instead of holomorphic function. So this is the case we are able to compute explicitly.
But this is giving you the atom at 0, right?
Yeah.
But if you were trying to find masses of other
then
atoms,
this equation will not be true anymore. So you have to change the things. It's not clear how to.
Put the real particle to 0.
Yeah, here you need
Yeah.
the wrapper to be.
but if you just defined HT equals IS, sort of.
Yeah, but the nice thing when you are on the imaginary axis is you have no real part. Whereas if you have a real part on an imaginary part, then you will have two intricate equations for the real part and the imaginary part, and
So
each
they
one.
both
Yeah.
move, do they? Okay, right. Okay. Just couldn't see that.
Yeah, sure. So for matching, there is a very nice result from Karp and Sipser, again for the Erdős-Rényi random graphs. So in my regime, the number of uncovered vertices in a maximal matching is given by this expression. And you see that this is where P is the smallest solution of the twice the iterate of the first problem on geographic game. Okay? So I can give you, this is exactly the same picture as I showed you before. This is the smallest solution that appeared in the Karp and Sipser algorithm, and this is the number of uncovered vertices. Okay, so there seems to be a link between the two. And here is a small exercise. What is the number of uncovered vertices in the maximum matching of these three? So this is still the same three. Okay. So the answer is again given by the first example I did show you, which is a leaf removal algorithm produce a maximal matching.
Could you please call the definition of the maximum?
Maximum matching is a matching with a maximal number of blue edges, or
Matching
minimal.
means we are only allowed to match neighbor.
Yeah.
Can you go ahead?
A matching is a subset of edges with. Okay, so in order to analyze this problem, we took the point of view of physicists. So actually, this has been done in the physics literature by Lenkas Belerova and Marc Lelarge. So, and what we do is we consider the Gibbs small measure associated to the matching. So the defect energy of M is denoted by h of M, and I guess I wanted to stick to the Hamiltonian version of the physics literature. So the energy of a matching H is just the number of uncovered vertices. So you want to minimize energy. Okay.
High energy, small lambda or big notation? High, low energy, and lambda. How they related? Which
Lambda?
you have parameter lambda.
Yeah, lambda is, I mean, for the moment, it's just you give me a finite graphs and I define this Gibbs measure.
You want high temperature, low temperature.
So the temperature for me is this Z. Okay.
Any.
So I do everything actually. Okay. So the temperature, well, when Z is 1, this is just a uniform measure on all matching of the graph. Okay. And when Z tends to 0, this converges to the, when the graph is finite, to the uniform measure on the set of maximum matching. So this is what you want to compute, the 0 temperature of this guy. And just to add one more notation, which is quite important, this is what is called in combinatorics the matching defect polynomial. So this is just a normalizing function for the Gibbs measure. Okay. So problem is we want to show the convergence of this quantity, which is the average with respect to the Gibbs measure of the energy. So the number of uncovered vertices in a matching taken according to the Gibbs measure at temperature Z. Okay. So the question is, does this converge as n tends to infinity when you take a sequence of graph like before? So there are some results for the 0 temperature directly. So if you consider directly the uniform measure on maximum matching, so the first one I gave to you is about the one of Karp and Zipser, and there is a recent extension of Bowman and Fries. And there are some results when the temperature is positive, but under restrictive assumptions. So that they are not able to deal with, say, Erdős-Renyi graphs, for example. So here's my one-slide explanation of what people call the cavity method. So the first thing you have to do, as for the rank or the empirical measure, is to write this quantity as a contribution of a sum of contribution of each vertex. So this is easily done because of the linearity of expectation. Okay, this quantity is just the sum of all vertices. That's the probability under the Gibbs measure that the vertex O is uncovered in your matching. And now it's fairly easy to show that this marginal distribution can be expressed in terms of the polynomial I showed you in this form. Okay, so this is straightforward calculation. And now there is a nice recursion for the defect matching polynomial. So this is just the definition of the normalizing function. And if you divide the sum by matching who left uncovered the vertex O, this is this contribution. And then you have to sum all other contributions when O is matched to a vertex V. And this is exactly this contribution. Okay, so this is a basic recursion true for any finite graph. So if you take this formula and this one, you end up with this nice recursion where this quantity, okay, is exactly the probability, the marginal probability for the vertex O of being uncovered at temperature Z. Okay, so this looks I mean, if you are looking now on a tree, say, you are removing, it's exactly the same kind of thing that I did before for the computation of the Stochastic transform. And you will end up with a nice RDE. And it's fairly easy to show that if you have only one solution to this RDE, then this quantity will tend to the mean value given by this RDE. Okay. So here, I just wrote the fixed point equation for the distribution f of z. So here, z is fixed, okay? So I'm just looking at a finite temperature, positive temperature. And I can iterate once, and you see that what is interesting, when z tends to infinity, you end up exactly with the same RD as before for the rank, for the size of the kernel, actually. Okay? So you see that it might be, you might be able to use the results you had for this RD that you already did study for the size of the kernel. The problem is, now here I'm looking at fixed z and not on the space of holomorphic function. And this is crucial for me, because otherwise I'm not able to show that there is a unique solution to this fixed point equation. Okay. So here is exactly the same slide as before. Okay, I'm solving the RD at 0, and you have a one-to-one map between the record of this function. So if you do the computation for Harder-Schwenning graph, you end up with a unique solution, and it corresponds exactly to what Carpenter did. And if you look at the recent paper of Bowman and Fries, they have a condition on the degree distribution which ensures that f has a unique optimal. So you can recover basically all results which are known so far. And now there is one case which is still open, corresponding exactly to the case which was open for the size of the kernel. Okay, when you have more than one historical record for the function f. So happily, it's not an open problem, and we managed to solve even this case by looking at positive temperature. So here is how it works. First, I'd like to say why it's nice to look at RDE at positive temperature, and why you have most of the time easier result for high temperature regime. Is that if you look at the property of the map, you are looking at a fixed point of this map. When the temperature is high enough, then you have a nice contracting property. Okay. So when Z is large enough, then you are sure that by iterating your map, you will end up at the fixed point equation. The problem is, I don't know a priori that this function is holomorphic anymore. So knowing things about the high temperature regime will not tell you anything about the low temperature regime. And here is something which is magic. It turns out that this function will be holomorphic, and actually it was known quite a few years ago. And this is the theorem of Feynman-Lib, which tells you that the matching polynomial never vanishes on the whole white part of the complex plane. Okay, this plane. So basically here, in the case of the rank, I was using heavily the fact that the operator was self-adjoint, okay, in order to get this holomorphic function. And here I'm using this fact to show that this function is always holomorphic. So if you can prove something at the high temperature regime, in particular uniqueness, then you have uniqueness on this whole space. This is given to you for free. Okay. So you know that this RDE, this is basically exactly the same as the one for the rank, but well, you have to a small change of variable as a unique solution. And for any positive temperature, you know that the energy will converge because there is a unique solution to your RDE. Okay. So now the whole problem is to try to let the temperature goes to 0. Okay. I'm here, I'm letting n tends to infinity. I can define an object on the tree at positive temperature. But what I'd like is to look at the object on the finite graph when the temperature goes to 0. So does it match with the same object when on the tree when the temperature goes to 0? Okay. So a priori, the solution you get on the tree, okay, so the zero temperature RDE, which is written like that, is just an upper bound for the quantity you are computing. Okay, so this gives you an upper bound, and for the rank we do not have a lower bound which matches. So here there is a very simple trick that allows you to close the gap. You have to consider the entropy of the law, and since you are considering a discrete model, the entropy will be bounded. Okay, so the entropy is always smaller than the log of the number of matching, and the number of matching can grow exponentially with the number of vertices. When you take the log, it will be linear, okay, and when you divide by n, it's constant. So with this very simple trick, you end up with a lower bound for the quantity you are trying to compute at 0 temperature, because this is bounded, and when z goes to 0, it vanishes. Okay. So the upper bound that you did compute does actually match the lower bound. So here is a summary of my last story. So this is a case where basically we are able to solve all the problem, and things are quite clear. So if you take a graph that converges to a Galton-Watson tree, then its matching number, so the number of uncovered vertices in an optimal matching, will converge, and you can express it as a function of the limiting tree. Okay. So the simple case which was done in the lecture before corresponds to the case where you have only one solution to the 0 temperature RDE. And this corresponds, if you go back to the interpretation of the core, to the case where the core actually does not matter and there is a perfect matching on the core. However, what we found out is that if there are more than one solution to the RDE, then there will be a positive fraction of vertices of the core which will be uncovered, whatever the matching you will look at. And actually, this disproves a quite famous conjecture of Normale on unmultiplicity of random graphs. So Normale was claiming that if the degree is bigger than 3 for that kind of model, then the graph is Hamiltonian. This cannot happen because of this. And we have a new conjecture which relates to this, that when you have only one solution, then the graph is Hamiltonian. So I don't have much to say again about the second story. We are able to compute the limit of the rank only when you have one solution to the RDE, and this corresponds to the case where you have a perfect matching on the core. Okay, outside this situation, we don't know. We have an upper and lower bound which do not match. Alright, going back to the first story, so the game on the graph. So there is a very nice interpretation of the game in terms of matchings. So on a finite graph, Alice wins if and only if every maximum matching covers the starting point. So you see here on the left, if say Alice starts here, then the optimal strategy for Alice is to follow actually the maximal matching. So to move here, and then Bob will have to move here, and then you will move here, and Bob will lose. Well, in this case, whatever Alice do, Bob will follow the red links and will win. Okay, so this is fairly simple to see. So if we go back to the very first topic about the Poisson Galton-Watson tree, this corresponds to Erdős-Rényi random graph, and you may ask if you play undirected vertex geography on Erdős-Rényi random graph. So this is a finite graph, so there will be a winner, okay, for sure. If lambda is less than e, then you know that the core is empty asymptotically, so the probability of winning is given by you by this Lambert function. But when lambda is bigger than e, then even if you know that the core will be matched, okay, there will be an almost perfect matching on the core. This only tells you that the game will basically explore the whole core and then finishes and we are not able to say if Alice and Bob do win, and it's very likely that this information is actually not local, and you need to do hardcore combinatorics in order to compute this quantity. Okay, that's all right.
the formula for the largest matching? You rederive it using Normale?
Yeah, that's exactly what we found with the RDE stuff at 0 temperature. So you end up exactly with the same with this result. Yeah. So the fixed point, I mean, if you do the computation, you end up exactly with. So if you want, we have a new proof of Carpenter result.
If you play the same game, but rather than removing vertices that you visited, remove edges, it's a completely different story, right?
Yes. So actually, so it's the case I did mention here. So this problem has been studied in computer science. On this case, because there is a one-to-one map between matching on my game, it's known that to find a maximum matching is polynomial in the size of the graph. Whereas if you do what you say, then the problem becomes much harder. I think it's p-space. So it's completely different story. All right.
No questions. Excellent.